Okay, so today we're going to finish up our discussion on continuous functions, and then we'll discuss the first homework. Okay. So just remember what the definition of the continuous function. It's actually so much nicer than the epsilon delta. I mean, it's just so easy to understand. Just the inverse image of an open set is open. That's all you need. And that's how you prove continuity. Okay. And so we're now at the part of the class where once you define continuity, you've got all the rules for making continuous functions. So notice there's nothing here about arithmetic. That's because a general topological space doesn't necessarily have arithmetic. You can't necessarily add or take roots or whatever. And so when we get to metric spaces where we have such things, then we'll talk about it. This is just kind of general. So the most trivial continuous function is the constant function. No matter what space we're talking about, a constant function is always continuous, because just think about it. What's the inverse image of an open set? It's going to be open because it's going to be one of two things. It all depends, right? So if we're mapping everything to y naught, it all depends whether y naught is in that open set or not.
It's either empty or the entire thing.
Right. So trivially, and they're the only two sets that are guaranteed to be open for all topologies. So the constant function is the only function which is guaranteed to be continuous for all, no matter what we're talking about. The second one is also pretty straightforward, the inclusion map. So if you've got a subspace of X, the inclusion function J from A to X is continuous. Of course, we've got to think about what topology is going on. In this case here, of course, we're talking about the subspace topology, which is the topology it inherits from X. So again, let's think. What is the inverse image of an open set in X?
What is the inclusion function? I couldn't find that.
So the inclusion function is just the that's a good question. So J of X, J of A equals A for all A in A. It's just the identity function, right? But we're just thinking of it as putting the subspace into the big space. So the inclusion, so for like in R2, you've got R, so there's inclusion of R into R2. Well, it's a bit more subtle than that, because it's not necessarily the identity function. What's the inclusion function, for example, R2 into R? Well, it would be, you have to put it in X somehow. So J of 1, maybe we put it in 1, 0. That's an inclusion function. Okay. So yeah, so the whole point is that you're putting it into the big space. So it's kind of like the identity, but it's not really, because the way things are written in X may be different from the way they're written in A. And if you think about it, there's lots and lots of ways in which you can include R into that. But typically what we're thinking of is, we've got an idea of what A is. So we might think of R as the X-axis. So the X-axis is a subspace of R2, and the inclusion is just putting that thinking of the space in the bigger space. Okay, so what is J inverse of U then, where U is so for example, think about this. So here is R and R2. Here is our set, open set U.
In that case, I'm going to help that interval the real line.
It's U intersected A.
Right.
And that's exactly the definition of open sets in A. So that's pretty, again, that's a pretty trivial proof. The third one is also pretty straightforward. Composition of continuous functions are continuous. And so what are we going to do? Well, we're going to show we've got some U in Z, and we pull it back. We want it to have some open set in X. Well, pull back U to what? To W, Y, sorry. We get a V, an open set V in Y. We use continuity here. We pull back V from here, and we get an open set X. So that's pretty straightforward. Next, we get some kind of more, oops, sorry. Restricting the domain. So this is really I guess this is just another flavor. It's of two. It's kind of like it's technically different, but morally it's the same, right? So here, instead of thinking, so here we're so here. So really, what is it? Oh, we can think about it as, what is it? It's a composition, isn't it? Restricting the domain is a composition of F with J over here. And so since both are continuous, the composition is continuous. Sorry. So yeah, restricting the domain, that's different from inclusion, but it's what happens when you compose F with the inclusion map. So it's just restricting the function to our subspace. Well, we can do that with domain. What about the range? Well, what we can do is we can change the range as long as the image doesn't, so we can, if we have a continuous function from X to Y, and we have Z as some subspace of Y containing the image, then just restricting it to Z is not going to change things as well. And also, furthermore, if you change Y to Z to something bigger, again, that's going to be expanding the range. You're going to still get a continuous function. That's and again, it's the same kind of proof. Because what happens? So this is a subspace of Y, and so open sets. Now you want to pull back an open set in Z back to X. Well, Well, an open set there is of the form, what is it, the form of it? Z intersected an open set of Y. And then when we pull that back, since Z actually contains F, when we pull it back, we'll get an open set in X. And then finally, we get a local formulation of continuity, which says that a map is continuous if X can be written as a union of open sets such that F restricted to each open set is continuous for each alpha in our what do we call those? Indexing set. Yep, exactly right. So let's just fully write out that proof. So we've got X is equal to union of U alphas such that F restricted to each U alpha is continuous. And so V is open in Y. And F inverse of V is intersected with our open set U alpha back in X is going to be just the restriction of F to that open set. And so since this is open in this set here, it's open in X. And then F inverse of V is then just equal to the union of all these open sets. And so since it's a union of open sets, it's itself open. Okay, so that's all pretty straightforward. Second last thing I wanted to talk about was the pasting lemma. And this is something that comes up all the time in calc, right? So you've got X, our domain, it's a union of two sets. And we've got a function on one set and a function on another set, and we want to paste them together. When can we be guaranteed that we have a continuous function? Well, as long as they agree on the intersection. As long as they agree on the intersection, then you just define the new function by h of x equals the function on one space whenever you've got an x in there, and it's equal to the function on the other subset whenever your x is in there. And since we've got this guarantee, since we have this equaling on the intersection, we don't get any troubles. So this is the sort of like the standard thing you've seen in calculus. And so all you've got to do there is make sure the functions agree at the intersection, which in this case will just be a single point. Okay. And so here's an example where they don't agree, and we don't get a function even, right? Because it's got two values at that point. And then we've got, this is also an example. So we've split it up into X, A union B, and they agree on the intersection because the intersection is empty, but it doesn't work, right? Because we need both sets to be closed. And the proof actually works if both sets are open. but it won't work for one closed and one open. Let's go through this pasting lemma then. So let's say we have a closed set in Y. So, because remember, we can just as well prove continuity for open sets and closed sets. Well, that's going to equal F. It's going to equal that union of closed sets. This is closed in A. This is closed in B. But this is also going to be closed in X, right? Because A is closed in X. So that's the union of two closed sets. So it's actually closed. Okay. Oh, before we go, why is this set not continuous? I'm not thinking about the calculus thing, but from our point of view. It's actually in the, there's a hint there in the diagram.
Yeah. This image should be open set, say from like a really small positive number to a really big. Just that, yeah, that open set right there. The image of that is closed interval.
Well, it's closed
Closed at one side.
At closed what? Yeah. So yeah, we can see that this is not continuous because the inverse image of this open interval is a semi-open, half-open interval there. Okay, and so the last thing about continuity is maps into products. So let F be a map from A into a product given by F of A equals F1 of A, F2 of A. So these are the coordinate functions of the function. Then this is continuous if and only if the functions themselves are continuous. Before we go on, there's actually no useful criterion for when the product is in the domain. So maybe you've seen this one. So consider this function. Xy equals something like xy over over x squared y squared if x, y is not equal to the origin and it's equal to 0 if x equals 0 and y equals 0. So this function here, if we just think of it as a function of x and restrict ourselves to let y be fixed, it's going to be continuous in x. And if we let x be fixed, it's going to be continuous in y. But this is not a continuous function because it's not continuous at the origin. Do you remember this one?
No.
So what does the function go to as we go down the y-axis? At the origin, what would the limit of the value be?
Because x is 0, so it's constantly 0.
Yeah. So in this direction here, it's 0. In this direction. Okay. But what about this direction where x equals y? If x equals y, then it's x squared over 2x squared.
Which is 1/2.
Right. It's constant. So it's equal to 1/2 along this contour. So the limit here is going to be, so this kind of set shows you that it's kind of hopeless going this way. But this way, it's very well behaved. And why is that? So let's show, well, if f is continuous, then the coordinate functions have to be continuous because, well, if we look at f1 inverse of u, for example, what's that going to be? That's going to be it's going to be something in the first coordinate. It's going to be cross something. It's going to be cross y. Instead of talking about, let me just write it down. Actually, if f is continuous, then trivially f1 and f2 are continuous, right? Because it's the composition of f with the projection map, and the projection map is continuous. Okay, so it's the other direction that's going to be harder. So how do we show that f is continuous if f1 and f2 are continuous? So what we're going to restrict ourselves to basis elements. So let that be an open set in x cross y. In fact, it's a basis element for the topology there. So u being open in x and v open in y. So we want to show that the inverse image of a basis element is open, and that will do it for us. Well, f inverse of this is equal to f1 inverse of u intersected f2 inverse of v. Right, and that's because if A is in the inverse element, inverse image of u cross v, then that's true if and only if f of A is an element of u cross v, and that's only true, right, if f1 of A is an element of u and f2 of A is an element of v. But these two sets are open by the hypothesis that f1 and f2 are continuous, hence intersection of open sets is therefore it's open. Okay. So let me stop recording.